Hello everyone, welcome back to ArcGIS channel. In today's lab, we're going to learn two fundamental concepts in GIS, coordinate systems and map projection. We first begin with the theory and then apply it in practice in ArcGIS. So let's get started. So this is a real shape of the Earth. As you can see, it's very irregular and bumpy. And the question is, how can I make any measurements on this irregular shape? And to address that, we need to define and fit mathematically a smooth surface like this to approximate the shape of the Earth. And this surface is called ellipsoid or spheroid, which is a 3D ellipse that has flattened at the polar areas. And this ellipsoid or spheroid is defined based on three parameters: the length of the major axis, the length of the minor axis A, B, and flattening factor. And flattening factor is how flat the polar areas are. After we approximate the real shape of the Earth with this ellipsoid, we need to link this and align it with Earth's surface. And this is done by datum. So datum provides a reference framework that specifies the position and orientation of ellipsoid relative to Earth's surface. So in other words, datum georeferences. Datum consists of an ellipsoid, so it has ellipsoid, and also it has origin and orientation. And orientations are defined based on prime meridian and equator. So ellipsoid is part of a datum. Okay, so here are the most popular datum and their ellipsoids and application. The first one is North American Datum 27 or NAD 1927. Is an old datum that uses Clark 1866 as its ellipsoid and has a very low accuracy, but is used for pre-1980s mapping. NAD 83, North American Datum 83, which is a modern version of NAD datum, and it uses GRS 1980 or GRS 80 as ellipsoid and has a much higher accuracy compared to the NAD 27. And the next one is WGS 84, which is another worldwide datum that uses an ellipsoid with the same name. So the ellipsoid is also WGS 84. And WGS 84 is the datum that is used in GPS as a framework and also for spatial mapping. Now that you have a datum, you have a framework to pinpoint location on Earth. And in order to do that, we use coordinate systems. So using coordinate system, which consist of axis and origin, we can define and present any location relative to an origin. So in GIS, we have two main type of coordinate system. The first one is geographic coordinate system or GCS, and the second one is projected coordinate system or planar coordinate system, or sometimes it is called Cartesian coordinate system. So GCS is defined on 3D sphere, as you can see, is defined on ellipsoid or spheroid. So it has a unique origin, and here is the origin for GCS. And locations are defined based on latitude and longitude. So latitude, angles of rotation from equator, and longitude, angles of rotation from prime meridian. For example, a location in South Carolina is 34 degree north or in latitude and 80 degree west of prime meridian. So it uses just angles of rotation. The values are between 0 and 180. The second type of coordinate system, as I mentioned, is Cartesian coordinate system or projected coordinate system or planar coordinate system. All are the same. And it is defined on a 2D plane, okay, on a 2D flat plane, and units are length unit. So for example, miles, feet, meter, and these units are actually distances to origin. For example, if I want to define this location, I have to say it's 50 miles from the origin to the right, to the easting, and 40 miles from the origin in the northing direction. Okay, so that's how we can define locations in the Cartesian coordinate system. Everything is based on length unit. It is not based on degrees. So if you see large values for coordinates, so most likely it's based on the projected coordinate system, okay? And if you see small values between 0 to 180, so most likely the values are for geographic coordinate system. Okay, so after you have a datum and you define the coordinate system, for example, geographic coordinate system, so the next step is map projection. So map projections are techniques to convert from 3D sphere like this, from the actually geographic coordinate system to 2D surface or projected coordinate system. So moving from 3D to 2D, it is called projection or map projection. And the question is, why do we need map projection? And the first reason is that we cannot always use globes or 3D surface or a spheroid because they are awkward in practice. For example, if I want to display something or draw something, or if I want to use it for navigation. So if I want to use it for navigation in cities with the scale, so the map scale is almost 1/24,000 in cities. So if I want to use this globe for navigation in cities, I need to always carry a globe with the diameters almost 500 meters or 1600 feet, so which is impossible, okay? So you need to have a 2D flat plane like this for navigation or for drawing or displaying. And also some GIS analysis, like in spatial analysis, network analysis, you have to measure some distances, some areas, and in order to do that, we have to use a projection coordinate system, not geographic coordinate system. So we need to project from 3D to 2D. However, when you go from 3D space to 2D space or project, there are always distortions, okay? All map projections have some sort of distortion. They can have distortion in area, distortion in distance, or distortion in shape. This is because when you move from 3D space to 2D map, you have to stretch or compress the globe or a spheroid, okay? So however, some characteristics can be preserved, okay? So there are numerous map projections. So for example, here is the map of the United States under different map projections. So some map projection can preserve shape, angle, distances or areas, but there is no map projection can preserve two characteristics or two properties or multiple properties at the same time, okay? So some map projections can preserve shape or angle. So they are called conformal map projection, and application is for navigation and also for military purposes, because in the navigation or military purposes, the most important properties that should be preserved is angle or shape, okay? So an example of map projection that can preserve angle or shape is called Mercator. However, in this map projection, distance or area will not be preserved. It will be distorted. Some map projection can preserve areas that we will investigate that in the ArcGIS. So for example, Albert equal area conic, which means that the relative area on the map will be equal to the area on the ground. And the application is in land use, and when you want to preserve in areas, and area is the most important aspect to be preserved in your project. And again, when the area is preserved, shape or distance can be distorted. So some map projection can also preserve distance from a specific point, but not across the map, and application in travel maps. For example, equidistance conic projection can preserve distance in specific directions, okay? And some map projections balance distortion, okay? So they can reduce or minimize distortion in multiple properties like area, shape, distance, and they are used for worldwide mapping. For example, Robinson projection is a type of map projection that reduces distortion in multiple properties at the same time. So you have to choose map projection depending on the purpose of your project. If you want to preserve area, shape, preserve distance, or minimize the overall map projection. However, these were a few map projections. There are tons of thousands of map projections that you can use for your projects. Alright, so now let's open up ArcGIS Pro and create a new project. So let's call it 5 projection, and I'm going to save it in GIS lab folder, create a new folder, 5 projection, and then OK and OK. So we are going to use US state map that we obtained from Tigerline in the previous lab. So if you go to map, add data, and then TL, so in under 4 proximity, so we had TL Tigerline 2024 US states. Okay, so here is the map of the United States for the entire United States. So the first question that I have is, what is the coordinate system of the data? Is it geographic coordinate system or projected coordinate system? So if you, let me close this one. As you can see, the values here are based on degrees, right? Western and also southern. Okay, so here, for example, I am in the, for the United States, I'm in the northern equator and western prime meridian. Here I'm in the northern but eastern prime meridian. Here I'm in southern and of the equator and eastern prime meridian, and here I'm southern equator and western prime meridian. Okay, so as you can see, the values are based on degrees and they are between 0 and 180. So this is a geographic coordinate system, and the geographic coordinate system, the values are based on latitude and longitude. Okay, so for example, if I'm in the South Carolina, as you can see, it's almost 80 degree western of the prime meridian, so that's a degree from prime meridian, and also that is measured on the equator, and northern degree from equator, so that's for the northern latitudes. So the units based on are measured on the globe or on the ellipsoid. They're not being measured on the plane, so they are angles of rotation. So the geographic coordinate system has been used for this data set. Okay, so the next question is, what is the datum or spheroid which was used to define origin, minor, major axis of ellipsoid, and how flattening the polar areas are, and what was the orientation, how they defined orientation? Okay, so for the datum. So in order to check that, you have to right click on the layer that you have in the table of content, and then select properties, and then select source tab. And if you go to the spatial reference, here you can see, so NAD 83, as I just talked about, that in North American datum 1983 is the name of the datum. The units is based on degrees, so it's a geographic coordinate system has been used here. And as you can see, as we already discussed, the spheroid for NAD 83 is GRS 1980 or GRS 80. And here is the length of the major axis and length of the semi-minor axis. So that are used to define the ellipsoid or spheroid. Okay, and also the flattening factor or inverse of the flattening factor. Click OK. Some type of analysis, especially in the next few labs, when we are dealing with distances, when we are dealing with areas, like in a spatial analysis, like in network analysis, we need to have a projected coordinate system. We cannot work with the latitude, longitude in those type of analysis. The question is, how can I change the coordinate system from geographic coordinate system to projected coordinate system? So in order to do that, you have to go to Analysis tab and then Tools, and here you need to type Project. So project projects spatial data from one coordinate system to another. So my input data set or feature class is going to be this one, Tigerline. So as you can see, it automatically identify the coordinate system, which is GCS, which means geographic coordinate system. It's latitude, longitude. And the datum was NAD 83. This is going to be the output coordinate system. So I'm going to save this in lab 5 folder, and I am going to call this US_project, which means that it's a projected coordinate system. The output that I expect should be based on meters or length unit, miles, not based on the latitude, longitude that I see here. And the output coordinate system, I am going to use, for example, Albers equal area conic for North America. So how can I select the coordinate system? If I click on here, select coordinate system, and here I type Albers. So it's an equal area, right? So under projected coordinate system, so as you can see, there are geographic coordinate system or projected coordinate system, and then I select continental, North America, and then I will select North America, Albers equal area conic. Okay, and click run. So you can see the difference because it already took the coordinate system from the previous data. So what we have to do is we have to open up a new ArcGIS and then load this projected coordinate system. Add data, projection, US project. Now let's compare. So as you can see, the shape is different. And look at the values. So let me close this. Look at the values. They are very large, 3 million. So it is based on meter, as you can see, is based on meter. And the values are like 1 million, 4 million, right? As you can see here. So they are meters, they are lengths. They are not based on the latitude, longitude. So that's a geographic. So here, if you compare this one is a projected coordinate system that preserves the area. And here, GCS, North American datum, that's a geographic coordinate system. So you can see the difference of the geographic coordinate system and projected coordinate system. So if we want to work with the, I don't know, area, some analysis that involve area or lengths, it is better to project the coordinate system. So this process is permanent. Okay, so when you project it, you will have a new feature class, you will have a new shape file that you can use it in your projects. Okay, so let's go back to the previous map. So using the project function, as I mentioned, you permanently change the coordinate system, but sometimes you just want to use it for representation, not actual analysis, okay? So in order to do that, so let me, what you have to do is that you have to right click on the map, which is the collection of layer, not just one layer. You have to right click on map, which is like data frame in ArcMap. And after you right click on the map properties, here you have to select coordinate system, okay? So for instance, I am going to use Robinson. And Robinson, as you remember, was a worldwide coordinate system, and it tries to minimize the overall distortion, right? So if you go to projected, world, and Robinson world, apply and OK. So here is the map of the United States under Robinson map projection. And also, for example, if I want to use Mercator, okay, so as you remember, Mercator preserves the shape, but area or distance are distorted. So if you go to properties, coordinate system, and type Mercator, and under projected coordinate system, word, and Mercator word, apply and OK. So let's look at the map of the US. The shape look normal, right? But look at the size of the Alaska. So it's almost it's over half of the United States, right? So it doesn't preserve area, but it preserves shape or angles, okay? So another one that I'm going to check, for example, Albers. And Albers, as you remember, is an equal area projection, which means that the area will be preserved. So if you click on continental, North America, and North America, Albers equal area conic, apply and OK. So here the area will be preserved. I would like to investigate whether the area of South Carolina is preserved under Albers equal area conic. Okay, so if you right click on if you open up the attribute table and then create a new field, let's call it area. Okay, with the data type of float or double. So area data type of float, close and save it. So it creates an empty field, and now I'm going to use calculate geometry to measure the geometry, which is area, right? So for this one, I'm going to measure the area, geodesic area, based on square miles. Okay, and under what map projection? I'm going to under what is the current map projection? Albers equal area. So I would like to see whether the area is preserved or not. So it has to be almost the same. Like maybe there are a few miles different, but it's fine. Click OK. And now let's look at the area of, for example, I don't know, South Carolina. So what is the area of South Carolina is 32,023, right? So if I Google, so as you can see, it's almost the same. So Albers equal area conic was able to preserve the area of the South Carolina, right? Or you can also check the other areas for the other states. So now I would like to use 3 different map projections. For example, for US continent, I would like to use US contiguous Albers equal area projection for Alaska, which is Alaska Albers equal area conic. And for Hawaii, I would like to use Hawaii Albers equal area conic. Okay, so let's begin with the continental US. Okay, so here we have US continent, and I am going to, so let's say you have created a map, doesn't matter symbology, or does it have symbology or not. So I'm gonna click on insert, new layout. I'm gonna use the horizontal map, horizontal paper. So, and after that, I am going to insert the map of the US continent. So let's say this is for US continent. Okay, so let me uncheck the word map. So here's the map of the US. If I go back here, map and properties. So I'm gonna use Albers, but for continental. So continental, North America, and I'm gonna select US contiguous Albers equal area conic. Okay, apply and OK. So here is the map of the US under this projection. Okay, so map of the US continent. So I am going to right click here, activate, make it a bit larger. Okay, so uncheck this and then close this. And so here is the map of US under Albers equal area conic, activate, and then I can move it here. So I am going to copy and paste this map. So if I go to the view catalog pane, and I have this map for the US continent, so I'm gonna duplicate this. I'm gonna call this Alaska, and double click. And for Alaska, if I want to change the coordinate system, go to the properties, coordinate system, and here I type Alaska Albers equal area conic. So continental North America, Alaska Albers equal area conic, apply and OK. So here is the map of Alaska under Alaska Albers equal area conic, right? So if I go back to the layout and insert, I can add the Alaska here. So create another map here. So here is the map of Alaska under Albers equal area conic. So I can also remove this border. So if I want to remove the border, I click on properties here for the border, and I'm gonna say that use no color for the border. Okay, so that's for Alaska. So how about Hawaii? Again, I'm going to go to the view catalog pane, and I'm gonna duplicate the map for US continent, and here I'm gonna call this Hawaii, and double click. And for Hawaii, I have to use the appropriate map projection, which is for Hawaii and continental North America and North Hawaii all equal area, conic, apply, and OK. So find Hawaii, which is here, and I can go back to layout, insert, and insert Hawaii. All right, so I was able to create the map of Hawaii, US continent, and Alaska under the appropriate map projection. Okay, so the next thing that I'm gonna do is I'm going to add graticule. So what are the graticules? Graticules are networks of latitudes and longitude lines over your map, and they help user to easily understand the geographic locations. Okay, so under insert, it is next to the map frame. So here, so you have to select the map frame first, and then here is graticule. So if you click on graticule and add, so as you can see, this network of latitude and longitude line. For example, here, this one, this state, or I don't know, like for example, Ohio is between 80 western and 85 western on prime meridian, and also, and maybe like 37 and 40 something, 43, 44 or 45 degrees of the northern hemisphere. Okay, so this state or this location falls in this between these latitudes and between these longitudes. Okay, so how can I have, like for example, I want to do some changes to this graticule. Okay, so if you look at the graticule, it has been added to the table of content. When you select it, properties, so in this window, if I go to the second tab here, components, so I can have control on different components of this, or I can add or remove some components. Okay, for example, if I want to have some labels to the corner, okay, so if I click on add, I can add corner labels. Okay, so as you can see, the corner label has been added. If I want to, for example, make it smaller, I have to select and click on symbol and make this, for example, smaller, like 8, the font size. As you can see, I can add the corner label. So for other labels, so for example, this one, if you want to, I don't know, if you want to remove the northern labels, okay, so northern labels have been removed. If you want to remove the eastern labels, right here, or western label, and so on. Okay, so that's for the label. Another thing that you can do, for example, the ticks here, these are the ticks. So you can also mention that what should be the distance or interval between the ticks. Okay, so in order to have control on the ticks, I think you have to go back here, uncheck automatic adjustment for the interval. Now I can have control on the text. So for example, if I want to change it to 10 and then 10. So how about for the labels? So if you look at the labels, which are, for example, for north, it starts from 20 and then 25, 30, north 35, and so on, right? So for the labels, it says 5 degrees, so make sure that you have to uncheck automatically adjust, and then I'm gonna change this, for example, every 10 degrees. Okay, 10 degrees, look at the value, 30, 40, 20. Okay, and also for the labels, interval for the latitude is also the same. Okay, so for example, 90, 100, 110, and so on. Okay, so for the text, every 50 minutes. That is based on the minutes, and tick 1, and also for the ticks here every 10 degrees. So you can have control, and you can say that which one should be visible: north, south, east, west, and so on. So that's how we can add the graticule to your map.